She here yet? I don't know where that sound's coming from. Did y'all hear that or just me?
I heard it.
Now what? Okay. Hopefully everything's okay. How many participants do we have right now?
30?
30? That's about. Hopefully get more. You got that message from me, right? Email with the Zoom link?
Yeah.
All right. Well, if you want to turn on the screens, it'd be great. It would help me. 30 people is not a lot of people, but I understand there's all sorts of things going on. The late shows. I have no idea who's unmuted. I looked, I couldn't find. I don't know where that sound's coming from. But all right, go ahead. Do you all see a shared screen over here or not? Just tell me.
Yes. You see a notepad.
Yeah, and what I was going to do is go through, starting with a couple of examples, unless somebody has a question, a specific question about this. I'm going to just do this if I can. We're in chapter 5, and I gave you, this is now three-phase power. So the idea with three-phase power is you have three phases, and if all the phases have an identical load and the same voltage, then the best thing is the average power is equal to the instantaneous power delivered to the loads, and that is important. So if I go here and do problem, I want to start with problem, unless somebody has something else to tell me, 537. So in problem 537, if you want to take a look at it, you can open it up in OneNote. That's there. I didn't mean to get that up there. In OneNote, 537 is this problem. It says an ABC sequence three-phase voltage source. That just means it's in a Y configuration, basically. Is a balanced Y and has a phase voltage of this. It doesn't say anything about the load. It just says it gives a magnitude of VAN as 120 at minus 45. Can everybody see this okay?
Yeah.
I mean, something, yeah, okay. You good, good, good. And the more information I get, the better it is for me, and hopefully the better for you. If you want to turn on your cameras, please do. I know people are shy. Sometimes people are eating lunch. Sometimes people just don't look the way they want to. But if you do, it helps me. And I don't care what you look like. So if you take this, the idea was we're going to go just get VAB next. Now, in the PowerPoint, if you looked at it, it said to get the voltage between the A and B line voltages, you simply multiply 120 by square root of 3 and add 30 degrees to that. How many remember that from the PowerPoint diagram?
Wait, is that unique to the ABC or is that?
It's just if you go from Y to delta, the only thing you do is multiply the square root of 3, or from line to line, and then add 30 degrees. So what I'm going to say is I had VAN, and VAN was 120 at an angle of, and this one it's minus, this is 537. At minus 45 degrees, sorry. To get VAB, this would be the AB line voltages, or VA minus VB. That's not important. This is. It would be the square root of 3 times 120, and then you would add 30 degrees. So this would be VAB would be equal to 207 about. You can check me on that. and it would be at an angle of minus 15 degrees. Y'all follow me on that?
Yes.
All right. Now it's, oh, by the way, is that Jessica, wherever you?
Yes, sir.
I'm looking, oh, there you are. I'm just gonna allow you to record, all right?
All right.
All right. Anybody else that wants to record, just tell me, or I'll make you a co-host if you. In other words, what I'm trying to do is make this as easy for you to get as possible. If you want to record your own versions of this, please do. And I'd appreciate for the people that are recording to put them on YouTube with some link to the group me so everybody can view them in case Canvas or in case this, I call it the cloud of Zoom crashes, which can happen. It's being heavily used. So this would be VAB, and the units are in RMS voltage because we're in power. Agree?
Yeah.
That's
Yeah.
as simple as that. What would VBC be? Notice I take the last letter of the AB phase and I put it here, and then take the next letter is C. What would the magnitude be, anybody? Anyone at all? Same as before, right? 207. The magnitude will always be the same for this if they're delta, or I should say if they're delta or Y phasings, the voltage magnitude will be the same. Now, what about the angle? Anybody want to try that? Anyone at all?
Angle is going to be minus 135 degrees.
Well, what did you do? It would take this and you would do what?
Subtract 120.
Exactly, subtract 120. So that would be minus 135. Who said that, by the way? I can't.
Josh.
Josh, you're right, correct. How about somebody else for VCA? Remember, I take the last letter, put it up here, then I'm rotating. I'm going technically clockwise, pardon me. Magnitude would be class
207.
207, and angle
105.
And what would you do? You would do what? You would subtract. Technically, you could add 120, right? That's an allowable thing. But no, I'm sorry, not 120, 240. But here you're going to what? You're going to subtract what? 120. So it'd be minus 135 minus 120. I think that's what you meant to do, and you were going to then make it positive. Am I right about that?
Yes.
All right,
Yeah.
and that would be what? That's 255, right? Minus 255. Is that right, class?
Yes.
Right?
Yes.
Now you could add, I mean, if you want to, you can add 360 to that if you want to, all right? And then you're going to get a positive value. Do you follow me?
Mhm.
All right, I wanted to do that. Is everybody clear on that?
Wait, so why do you multiply 120 by the square root of 3?
Remember, we're talking about a difference between AB and AN. Now, I'm glad you asked that, whoever asked that. If you looked at the PowerPoint, and I'm going to bring up PowerPoint over here. Can you all see the PowerPoint? People?
Yes.
Yes.
Okay, if you look, that's VAB. This is a diagram where you have real and then imaginary axes for all the voltage. VAN is just equal to, it's just whatever it is at 0 degrees here. Now, I'll say one other thing. The thing is, VAB will always be at 30 degrees ahead in a magnitude here of the square root of 3. And who asked that question, by the way?
That was me.
All right, John, the real reason is if you look at this geometrically, I mean, VAN or VAB is VAN minus VBN. Well, here's VAN shown clearly, and here's VBN, right? When you do a subtraction, you reverse the direction of the vector and add them together. Therefore, you would get that. Can you see that okay, John? Or JT? Pardon.
Yes.
Okay, everybody see that? Any question about how I got the magnitude? Now, the thing I want to make sure is whatever VAN's angle is, whatever this angle is here, if it was 30 degrees, 50 degrees, 60, you have to add 30 to get VAB. 30 degrees to that angle to get the correct angle. And the magnitude just goes up by the square root of 3. Are we good on that, everyone?
Mm.
All right.
So the imaginary component doesn't change.
Well,
like the magnitude of the imaginary
you're
component.
confusing yourself. There is no real and imaginary I'm talking about. I'm simply magnitude and angle, right? I'm not going to break it up into a real and imaginary. I'm going to keep in polar. So the real part here, I mean, VAN is at 0 degrees, right? It's at 0 degrees, correct?
Yeah.
The magnitude is 120. Now, ours is not 0 degrees. Ours is minus 45, but here it's 0. So whatever that angle is, you add 30 degrees to the angle. Stay in polar. Don't ever go to rectangular for voltage, okay? All right. All right. So that's going to be just 30 degrees added to the angle, and the magnitude jumps by the square root of 3, and that's it in a nutshell. You don't have to worry about this garbage right here. I never do. Everybody okay with that? All right. And I can only see about, how many people do we have here? Just someone, please.
59.
How many?
59.
59. All right. Now, I can't see everybody. I can only see people with their cameras on, and there's only 3. Myself and 2 others. If you turn your cameras on, it makes my life easy, but if you don't want to, I understand. I will not force you. Anyway, that's the reason. Now, that's 37. Let's go through 538. All right, and I know this is going to seem very boring to those that did it, but please bear with me. Some of you may not have, for whatever reason. I just want to make sure everybody understands this. 538 in the book now says this. Same ABC sequence. You'll never have to worry about that. That means nothing to you. For all intents and purposes, it's standard electrical power delivery. Voltage source is connected in a balanced Y. Y is the way it is. It means it has a common ground. And it has a line voltage of VAB 208 at 175. Now they want the reverse. They want the phase voltages. Do y'all follow me? They want what we had before. So if we take VAB and divide by the square root of 3, we have the magnitude of VAN. And if we subtract 30 degrees, we have the angle. Does everybody follow me on that? So I'm going to do it right here just to make sure. Here we had VAB, and it really doesn't matter what the values are, equals, what was it, 208?
Yes.
I think I had 207. It's 207 point something. I think they rounded up to 208 to be accurate. And it's an angle of 175, right? So if I want VAN, does everybody see I take 208 and divide it by the square root of 3? Now I have the correct magnitude. And then the angle would be, what did he have, 175?
Yeah.
175 minus 30 degrees. Now, are we good on that so I can move on?
Yeah.
Any other questions about what, I mean, the transformation between, it's called this delta. That's the more appropriate name. That's a delta voltage. This is a Y voltage. And those are the symbols used, delta and Y. All right, now, the next thing I'm going to do, I'm going to go through problem 539, but I'm going to talk about this first. Here's where I go into a slower mode. The first 2 problems were trivial in my opinion. They say the 3-phase ABC sequence balanced Y-connected source is connected to a balanced Y-connected load. Now, I'm going to show you when you draw that, you do this. This is 539. You simply do Y, Y. That is always the way we're going to reduce everything to. There will be transformations to take delta configured power sources and delta configured loads to Y, Y. And we always go Y, Y. I'm going to say it one more time. We always transform any power system to Y, Y. Regardless of what you read online, I'm telling you the easiest and most personally accurate way to do it. So now in this one, thank God it is YY, it says that the phase voltage is 120 volts and they don't give an angle. So assume it's at 0 degrees. So here I'm going to just put it down. Here's VAN, it's 120 RMS at 0 degrees. Now, if they don't give you an angle, you always default to 0. Are you good, class? Now, the next thing they give you is the load impedance is 16 plus, that's the load, that's the thing that's receiving the power, 16 plus J8. So this is 16 and J8 ohms. And the line impedance is negligible. It means the impedance connecting the small a to large a, that's the transmission end, that's the receiving end, is 0. Also, this point is a small n. You can consider it ground. It's always small letters for the sending end, always large letters for the receiving end. Here, there'll be a capital N. Now, I have a question for the whole bunch of you that are watching. How many people have worked with grounding in any way, shape, or form? You've heard the term ground for either DC in your car or your house voltages in any way, shape, or form. You know that terminology and had to at least be aware of it, right? There should be a good chunk of you if you're in engineering. If you have worked with it, there's one type of ground that you have to be very aware of, and that's called an earth ground. Now, how many have heard of the term earth ground? Any kind of wiring on a house ultimately has to have an earth ground somewhere that makes it a very low, I'll call it impedance path for any currents to go to ground. And that earth ground, the earth below you, technically is the return path to the power company if any other grounds break. Do you follow me? You might say it's a safety measure, but there's more to this that I don't want to get into here. I'll talk about grounding later. God willing, I will at least. Anyway, from here, these two are effectively the same point electrically. So you might as well just do that. Got it? You don't have to worry. Some people put this little small dinky resistance there. Forget it. Don't worry about it. It's a short. Everybody? Now, the next thing they say, determine the line current. All right. Now, that's the catch. Here's the current right here, right? Now, just listen to me. That current is I small a large a, right? And it would be the I small a n. You all follow me that that's a simple series circuit? You all follow that? Class? Can you all, first of all, can you, maybe you can't
Yeah.
see.
Yes.
All right, it's very simple. What would that current be? Well, I small a capital A, which is I small a capital, or small a small n, pardon me, is equal to simply 120 at 0 degrees. I can drop that over 16 plus
You're out of
J.
focus.
Thank you. Plus 16. I wish you had an autofocus of urine so you could keep me there. Come on. There we go. Plus J8, right? Now that's a magnitude and angle. I'm going to calculate that. I'm ready to calculate that. I've got my octave here. So I got I equal to 120 over 16 plus J8. You can do it on yours. Times you're probably faster than me, most of you at least. And then I take an ABS of that. And I get 6 point, you can check me on this, 6.7082. Anybody want to confirm that?
I got 6.7082 at negative 26 degrees.
I'm going to take that. Yeah, I'll give you the minus 26 degrees about. How's that? Y'all with me? Now listen, everybody see what I did and why I did it.
There's more decimals to the angle if you need them.
Don't worry about that. This is strictly to show concept here. Y'all with me on that? Now take a look at the language again. It says a phase voltage. Phase is Y. You want to write that down? Go ahead. In your books, preferably, or on your notepad, or on OneNote, however you want to do, or wherever you keep your notes. Phase voltage is Y voltage, and that's 120. The load impedance is 16 plus J. That's IAN. Now, when they ask for line currents, right, you've got to be careful, and I will always specify this. That's I small a small n, I capital A, or small a small b. This is important. You see this. I'm going to get it from my PowerPoint so you see this. That current is actually going to go down by the square root of 3. Let me try to show you this. All right, here's what I just showed you. If you can see this PowerPoint, I showed you I small a capital A. Do you all follow me? Can you see this right here? I just simply took the load and divided it into the source voltage. But I'm sorry. Yeah, small a, and then there's B and there's C. All 120 degrees difference, just like the voltages, right? The A phase, to get the B phase, you're going to subtract 120. And to get the C phase, you'll subtract, he adds 120. That's the same thing, but you could subtract another 120 and add 360. And then he gets VAN, VBN. I don't want that right now. I'm looking for, yes, I want to tell you this. Tell you what, just tell you right now what's going to happen. I'm not even going to mess with the PowerPoints. Here's what will happen. It'll be this magnitude of this divided by square root of 3. So it'll be magnitude of IAN divided by square root of 3. All right.
We're still looking at the PowerPoint.
I'm sorry. I'm just checking out one thing. He had this here, but he's leaving it in terms of Z delta. All right, let me go through this. The I small a small b, this is the actual current that would be going down the line from A to B, and I'll get to this more, is going to have a square root of 3 reduction. Actually, let me do it this way. Let me just do this. For now, I want to just focus on IAN, and that would be I load. Do you all agree with that? I load would be I small a n. Are you with me? I don't want to confuse you too much. You all with me on that, class? And this, in fact, let me say this. This is correct. This is the actual current that flows down the line. All right, now I'll get to what I'm talking about we're thinking about in a bit to not confuse you. I want to do the next problem, and my opinion is this. The best way to learn this stuff is to see problems done and ask questions when you don't understand them. I try to present the theory behind it and then apply it, okay? Everybody, you with me so far with what I'm doing? At least with YY. Go to 540. They said if the line impedance in 539 is 8 plus J6, determine the line current. The only modification we're going to have, we put the source in, this is 540.
Can you move your paper down a little bit?
Yeah, thank you. We put the source in right here and put plus to minus 120. Remember, it's at 0 degrees and the default here is RMS voltage. Now he gives you a line impedance, and the line impedance is 0.8 plus J 0.6. So 0.8 plus J 0.6. Sometimes I use boxes, sometimes not. This is small n, this is small a, this is capital A, and then the load impedance is the same, so it's 16 plus J8. You could just draw a box there. And this would be capital N. Now, what I do, and I'd recommend you do, sometimes on the internet in real power problems, you're going to see a very, very small amount of resistance between these 2 points. Don't worry about it. For us, unless it's stated, it's a short circuit. All they want is this current. That is the line current, which is IAN, which happens to be I small a large a, if you take a look at this, right? That's I small a large a. They are all the same thing because it's a simple series circuit. Are you with me, class?
Is
What's the-
is that 11 plus J8 or 16 plus J8?
16 is from the prior problem. Did you all do these? I gave you the problems and the solutions. So if you look at them, if you've worked them, these should be fairly straightforward. What I'm looking for are questions from people that tried these things, and I'll try to answer them. Are you with me? All right. Now this current's what I want. It's just as before, only what will it be? I small a n equals to I line. And I like to put the a in here because it tells you what phase. That would be what? 120 divided by class 16.8 plus J, what? 8.6. And you can tell that's going to be reduced from the prior problem because now we've added more resistance and J impedance, right? Reactance. Correct, class? Are you with me? Just looking, you know it's going to reduce the current. What will it be? I mean, I'll take it from anybody. If you want me to, I'll work it. I'm trying to get you to do these things in real time with me.
Point,
6.36
Uh,
angle of minus
Jessica, say it again slower.
6.36. The angle is minus 27.12.
Okay, slightly different magnitude, slightly different angle, but very close. Agreed?
Yeah.
Now, before, the voltage at the sending end was the voltage at the load because there was no line impedance, correct? All right, now what is the voltage at here, right here? What is VAN? This would be called the load voltage. How would you get that? You can do it a lot of ways. Anybody want to tell me? This is a basic circuits problem.
So the one that you just calculated, the current that you just calculated times 16 plus J8.
That'll do it. I can take this, I small a n, right, times 16 plus J8. That'll do it. Anybody else? That's absolutely correct. Another method would be what? Take 120, right? Then divide it by 120 and divide it by these two combined, and then multiply it by this. That would be voltage division, but it's effectively the same thing as this, isn't it, class? So voltage division, what we just did here, are in fact the same thing. How many see that? All right, because voltage division implies you're calculating the current. All right, now that's 540. 541, if you don't mind, we'll do this one. All right, 541. It says an ABC sequence, balanced three-phase, Y-connected source with a phase voltage of 100 RMS, great, to a balanced Y-connected load. The per phase voltage, per phase load impedance is, so they give you the impedance, and that per phase I wouldn't do. I'd say it's YY, it's a Y load. Follow me? I would be very clear until you're more familiar with the language. So here, what you do is go YY right off the bat. All right, phase voltage is simply 100, or I'm sorry, this is phase voltage is 100. There is no information about the angle. And in fact, most of the time, you don't care about angle. If you're worried, if you're in the real power world, just care about the RMS voltage. However, if you're talking about all three phases, then the angle becomes important. So for this one, they said the source voltage here is 100. Just put down 100. And if they don't give you one, make it 0 degrees or omit it. That's volts. Then they say that they have a simple Y-connected load of 40. This is about as easy as it gets if you look at this, right? 40 plus J, what is it, 10, right? I'm assuming you have this available to you. This is 541. I should have shown you this first. Yell at me if you don't have it available and want to see it. It just gives you 100 volts, RMS, Y, and a per phase load impedance of that. That's a Y connected load too. And determine the line currents. And then the last part, determine the line currents if the VAN's angle is 0 degrees. So they do give you the angle at the very last part. By the way, this will look a little weird to you probably. Can you see how it's an angle sign there? And then VAN? So he's saying the angle of the voltage is 0 degrees. So that's what I assumed anyway. For this one, that would be small a, that capital A, that capital N, that small n. And how many see what that current is? That would be the line current or IAN. Anybody? I mean, what do you know it's going to be, guys?
Voltage over resistance.
Yeah, I mean, what is it going to be? Well, impedance, actually. It's 100, right? Over 40 plus J10, whatever that comes to. Are you with me, class? Can I see some? I need a little feedback here. I got a whole bunch of black screens with their microphones muted. I've got what, 1, 2, 3 people that are visible to me. And again, I encourage you to turn on your cameras, but if you don't want to, don't worry about it. I can only imagine. I mean, this is lunchtime, so I assume, well, roughly lunchtime. Some of you are eating. That's no, regardless of the reason. I hope you got it. Everybody with me? Next one. Let's do 42, and I hope this helps. Personally, this is the way I like teaching. Give the theory and then apply it to as many problems as possible in real time. If you want to give me the magnitude that you can, but you have solution, or I mean, just give me the answer.
2.42.
2.42 at what angle? It's
Negative 14.
Anybody else confirm that?
Yeah.
Anybody? You got it? All right, and you can use a thumbs up if you don't want to talk. 5.42, an ABC sequenced balanced three-phase Y-connected source supplies power to a balanced Y-connected load. Now, you can almost do this in your head. By now, some of you are starting to say, this is almost ridiculously easy. So it's a Y-Y connection, right? Now, when you look carefully, it says the line impedance is 1 ohm, only 1 ohm, no imaginary part. We're going to draw it. And the load impedance per phase, that's Y connected, is 20 plus J20. Are you with me? He's adding a little complexity. So we're going to draw that up in a second. But before we do, if the source line voltage, VAB, is 100 at 0 degrees, we can't use that directly, can we? If we want line current. Right? What do we need to do?
Divide by square root of 3.
Right, and
Add 30.
subtract 30, right? So now we come here and we say we have a voltage here, and this would be V small a n, which would be the magnitude of VAB divided by square root of 3. So it'd be 100 over the square root of 3. And since that's at 0 degrees, this would be at minus 30 degrees. You all with me, everybody? Next, he has a line impedance here of 1 ohm. So you can put just a resistor, 1 ohm. That's perfectly acceptable. That's small a, that's small n. Then this goes to capital A. That's where the load is. And it says the load is 20 plus J20. So it's 20 plus J20 ohms here, right? And that's capital N. And they want this, all right? They want IAA. And you know, that is, in fact, what? Isn't that capital A, capital N? That is the current in the load just by inspection. Do y'all agree with that? They're in series, it has to be. So again, how do we get IAE? Or we call it I small a large a, or I line. And that would be this voltage. You guys can give that to me, it'll help me. Square root of 3, right? And then this is at minus 30 degrees. And then this whole thing is divided by 20 plus J20. Now I can tell you a trick. 20 plus J20, I know the magnitude of that is going to be 20 times square root of 2. And I know the angle is going to be 45 degrees by inspection. Do y'all agree with that? If we had
Yeah.
like 1 plus J1, magnitude of square root of 2, angle is 45, factor out the 20 and you get this to save time. Agreed, class?
Yes.
Okay, are you with me, guys?
You say that again, I was copying stuff down.
Yeah, if you have 1 plus J1, the magnitude of that is square root of 2, and the angle would be 45 degrees. So if you have 20 plus J20, if you factor out the 20, you're left with 1 plus J1. The magnitude of that is square root of 2, the angle is 45.
Gotcha.
Now, this one you can kind of do in your head, maybe not exactly, but it says I, small a, large a would be what? 100 over 20, right? And that's what, 5, right? And there would be 5, and then you would have square root of 3 over square root of 2. Or just do it in your calculation. What about the angle? When 45 comes upstairs, as I say, it goes from denominator to denominator to numerator, it becomes minus 45, and now we have minus 75 degrees. Correct, class? Are y'all with me? I'm trying to get through this. What's the magnitude of that?
2.04.
Times 5? No, square root of 3 divided by square root of 2 times 5? What did you say it was?
Or 2.04.
I got 6.12.
You see, square root of 3 over square root of 2 is greater than 1. If it's multiplying 5, it has to be greater than 1. Say that again.
6.12.
6.12 at an angle of minus 75. Do you agree with that?
Dr. McGinty, I got 2.04 as well.
All right, now look, if you have 5 times square root of 3 divided by square root of 2, right? That's larger than 1, isn't it?
Yeah.
That times 5 has to be larger than 5, doesn't it?
But I was plugging in, rather than your simplification, I was plugging in the raw.
Mhm.
All right, 100 over square root of 3 divided by 20 square root of 2. Go ahead and do that. Oops. Wait a second. I'm sorry, I have these backwards. It should have been 5 square root of 2 over square root of 3. My bad. You probably are right. My bad. I had them inverted. That's probably, what is square root of 3 over square root of 2? 1.1.
1.22.
No, square root of 2 over square root of 3 part.
You just asked the opposite of that.
I know. Sorry.
0.816.
All right, and multiply that by 5. That's probably, this is not right.
That gives 4.08 instead of the 2.04.
Well, I'll say, I don't want to spend much time on this, but look at this. 20 into 100 is 5. Do you agree with that?
Yes.
And then I have square root of 2. Oh, divided by square root of 2. My bad. I'm so sorry. I'll slow down. So this is going to be 5 divided by square root of 3, square root of 2. And I am sorry. And it's still at minus 75 degrees. So you're probably right. The 2 point people are right. What did you get, guys?
2.04.
Yeah, that sounds right. 0.4 at an angle of minus 75, right?
Yes.
I'm sorry. I'll slow down a little. Are you good on that? But this is the essence of it right here. You take the voltage divided by the impedance. Oh, wait a second. Let me finish this correctly. Here's the problem. I forgot the 1 ohm. So to slow down and do it right, small a, large a would exactly be equal to this voltage, which is 100 divided by square root of 3. It'll be about the same at an angle of minus 30 degrees. Then it's divided by 1 plus 20, or 21 plus J20. My bad. It's not going to change it much, but that would be the exact right answer. And you've got the solutions, but you can give that to me if you don't mind. It's 2 about 1, or sorry, 2.02 about. Am I right?
The solution says 1.99
For what?
for the IAA, 1.99 at the angle of minus 73.6.
All right. If you do this, if you take 100 over square root of 3, this is the right equation. And Jessica, if you're looking there, you probably see this equation.
Mm-hmm.
He does have that equation?
Yes, he does.
So fundamentally, the answer is just this solved for. What did you get for this again? Did you
I
get?
got 1.99 at an angle of negative 73.
I think that's 1 point. That's what she had, right? 1.99 at an angle of minus 73 degrees. But again, this is just mathematically shoving the stuff in your calculator correctly. I'm sorry, I'm running fast. Are y'all with me on this class?
Mm-hmm.
Yeah.
Okay. Again, these are trivial problems when you understand what we're talking about, right? And what, by the way, this is AA. What would BB be? Anyway.
Offset by 120.
All right, subtract 120. Same magnitude, only offset or subtracting 120 from it in degrees. Agreed, class? When you're doing these problems, this will become self-evident, but I wanted to get through as many as possible today so you've got a good handle on it. Now, next thing that we're going to do is I'm going to jump to 43. All right, now let's look at this before you do anything. Please, everybody with me. All right, an ABC sequence balanced Y-connected source supplies a balanced Y-connected load. That's Y. Right, that's the way they're going to do it. Here they say if the line voltage at the source is, now that's line, not phase, so it's 240 at 0 degrees. We need VAN, don't we, class?
Yes.
So what do we do with this?
Divide by square root of 3.
And
Subtract 30.
Exactly. We're going to do it, but you all hear that, all right? This is AB. So on a test, don't make mistakes like I did earlier and run through it and then blow a lot of stuff. Slow down and just look. Here it's VAB is 240 at 0. The actual VAN that we will use will be 240 over the square root of 3 at minus 130. That's the voltage. The load impedance is 18 plus J12. That would be from capital A to capital N. And the line impedance is 1.2 plus J1. Do you notice how the complexity of these problems changes just slightly as you go down? Not major jumps. Follow me? They add a little bit more complexity. So when I do this one, right away, I go Y, and this is 5.43. Now I go ahead and do the load voltage here, and that's going to be a voltage here, plus the minus 240 over the square root of 3 at an angle of minus 30 degrees. Correct, class? Again, that's just, and that's small n, that's small a. That's just identifying the phase, A to N voltage. Now the line impedance in this one is 1.2 plus J1. I'm going to just write it like that. Then I'm at capital A, and then I have a load here of 18 plus J12. And determine the line currents and load voltages. Well, the only current I'm going to get is this one. We know how to get the others. This is small a, capital A, which is actually I, capital A, capital N. And what is that, class? We know from before. That's voltage source 240 over the square root of 3, right? Angle is minus 30. Then the total is what? 19.2.
Mm.
And it's going to be plus J, it's going to be 13, right? Now just leave it there for now. Do you all agree with me on that?
Yes.
All right. The answers are in the solutions. We could solve for this, but at this point, if you see this, you realize the only thing you need to do is learn how to enter this correctly in your calculators. I'm saying this again. Entering this information correctly and being able to solve it is pinnacle in this course. This is very unforgiving with engineers that don't know how to do that. Do you hear me, class? So I want to make sure you know how to use your calculators to get this kind of calculation correctly done every time, God willing, Lord willing, assuming, you know, your batteries don't go dead. And please, and I encourage you, please, 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 for the exam on Friday, make sure you have charged batteries, make sure you come early, get your sleep, and anything else you need to do. Anybody want to give me that?
Do you want it in polar or rectangular?
Always polar.
5.98 at an angle of minus 64.1 degrees.
Okay, y'all hear that?
Yes.
Okay, good. Now, remember, do the calculations in YY. Now I'm going to do, how much time I got to get? 7 minutes. I want to show you something. Next, bring back that PowerPoint if I can, and just mention something to you. Now, some of you are going to get a little frightened, but don't. When you work these problems, it'll be clear. Now, you see how, can you all see the PowerPoint? There's my first question. When you look at the PowerPoint, you all see this is a Y-connected load. It's obvious. It has a common point, a neutral, right? Anytime you have a common point like that, it's a Y-connected. This is a delta-connected load. You all follow me? All right.
Yes.
Why? Because it looks like a delta for starters, but there's no neutral, right? None of these have the same point for all the loads. Here's the thing with the value of the delta connected. I think he does it. He doesn't do it there, but I'm going to do it. He does it with a proof here. I'm just going to tell you. Here, get that out here and just show you. Without me going through the proof, if you take a, maybe I will go through it a bit. If you take a Y-connected load, like so, and call this ZY here, doesn't matter what it is, ZY here, and ZY here. All right, this is small, or this is capital A, capital B, capital C. That's all Y's, all symmetric. Here would be a neutral. And if we wanted to take that and make it into a delta, all right, so then they would have something where we'd have this. We want to make these equivalent. That's Z delta and that's Z delta. So these are Y's, these are deltas. And that would be capital A, capital B, capital C. And loads are like this a lot of times, real loads. Some are like this, and that's another discussion. So how do we get these two equal to each other? Now I want you to take a look at this, people. This is how you do this in the real world all the time for anything. When you're equating things, you simply see what the value would be in one domain and equate it to the other. If I go between A and C and I look at the resistance here, do you see, or the impedance, do you see how the impedance between these two terminals is 2 times ZY? You all with me? Because this is a dangling terminal, isn't it? All right, so it's just twice that. How many see that? And I know maybe I'm going too fast for some. Y'all with me? I got 2 people. Jessica?
Yes.
Okay. Anybody else see this? Is there anybody else out there? This is one of those tragedies.
Yeah, I see it.
All right. So that's that. What about between A and C here? What is the equivalent? Well, it's what? ZAC, right? This is what? I'll call it Z, small a, small c. Here, what do you get between these two terminals? Well, you're going to have this one in parallel with the series combination of that. So I have Z delta, right, in parallel with two Z deltas. How many can see that right there? And that would be ZAC. This is capital AC. You with me, class? Okay, thank you. Make me feel a little better. All right, now we equate these, all right? First, what is this really? I'm going to do this simply. This is what really? It's Z delta, right, times 2Z delta over 3Z delta. Do you all agree with that? I'm just taking this times this over this plus this, correct? And I'm equating that to this, which is 2ZY. This is not mind-blowing, by the way. It's going to be a very simple result. All right, some of you, and I realize I'm moving a little quick. Some of you can see that the 2's will cancel. All right, and a Z delta will cancel. And then lo and behold, you see that the equivalence is ZY equals Z delta divided by 3. And that's it. Or like they say, sometimes you need Z delta and you would take 3 times ZY. Are you with me? Now, what it means is the Y load is much less. It's divided by 3, the delta load. And that's the key to this. How many hear me and understand this? Are we good? Thank you, thank you, thank you. I realize it takes time to hit that thumb when you're writing. I do, but I appreciate the thumbs up, and I'm glad there's a very limited number of gestures. Anyway, now, so having said that, this is the last problem, and some of you may have to leave, but trust me, this is going to go quickly. Next thing I'm going to do is 544. This is where it gets better. Now keep up with this. I wish I had, honestly, another hour right now to just whip through this, but I don't. 544, an ABC sequence balanced Y-connected source supplies a balanced, Y-connected load. Talk on it. We'll do that one anyway. All right. Tell you what, let's do 545 for the last one. It'll be better for everyone. They say in a balanced, and if you need to go, this will be on the video. Here in a balanced 3-phase Y delta system. Now, right away, I'm going to show that. I draw this as I got a Y source, a delta load. Got it, everyone? But we're going to transform that load into a Y load. Y'all hear me? I just put Y delta. That load's delta, and it's specified as. So it says they give you a current I small, that's a line current. I give I small a large a is 8 at 13.13 degrees. So I small a capital A is 8 at an angle of 13.13 degrees. All right, that's amps is the default unit. Then they say if the line impedance per phase of the delta load, now you'll notice delta load is 36 plus J27. You follow me? We don't want to do that. We want to take this immediately and take it into a YY configuration. Are you with me, class? So what do we do with that load if we want it YY?
30 or some.
No, what do we have here? We have Z delta is equal to 36 plus J27, right? Remember the relationship, right? It was ZY equals Z delta over 3. Didn't we just prove that, class? I'm going to remember that.
Totally forgot.
Guys, I mean, do you? It doesn't, I mean, just remember it now. Do you all remember, at least jogs your memory? So we divide this by 3. That means the equivalent zy, which we want, would be 36 by 3, right? Or it'd be 12 plus j, 27 by 3, or 9. All right, now that's a y load. Now we drop yy, and I'm going to do this. I want to go back to, this is taking the original problem and then re-specifying it yy, because to get line currents, we do it in y. Everything we want, we do it in the yy domain, and then if they ask for things in the delta domain, then we go ahead and make the transition. And this one I'm going to do. How many people do I have left on here?
38.
Okay, 38, good. So I'm going to draw this in a yy. This would therefore be v small a n. My line impedance on this one was what? Nothing. Perfect. Now this would be small a. This would be n. Goes right to a capital A, and the load now is in a y configuration. The y configuration here is 12 plus j9. And that's going to be grounded capital N. And you guys can do that. That's fine. Now, what we want, or what they specify is this, right? Now, just listen. So I got this current, I, small a, capital A, right? Are you with me? Y'all
Yeah.
see it? Question for all of you. How do I get this voltage? V capital A N, anyone? You guys know it. I have a current, don't I? I have this current. That is IA, and I have this impedance, right? The voltage would be those two multiplied together. Correct, class? So I'd have V capital A N equal to what? I small a capital A times 12 plus J9. Do you all agree with that, everyone?
Yes.
To the left, people?
Yes.
Believe me, I'm doing you a favor here. All right, now, if you want to, you can give me that, but it's not necessary. I can do it, but I mean,
120.
say it again.
120, an angle of 50.
50 degrees. Anybody confirm that? Anybody at all? Thank you.
What was the current?
Right here. It's 8 at 13.13 degrees. Is it hard for you to get OneNote up, or? I mean, my advice to you is print out the problems. That's my advice, if possible. So you can refer to them during the lectures. It should help you. Now, when we have this as VAN, isn't that also equal to V small a n? Simply because they're hooked in parallel, aren't they, class? You see that?
Mhm.
I can't bring up my chat for some reason. Oh, wait. Isn't that? Oh, this is from earlier. Anyway, is everybody okay with that?
Yes.
Now remember, what we're doing with this is an impedance, so it's divided by 3, not the square root of 3, when we make the transition from delta to y. Now, once we have VAN, here's the $64,000 question. How do I get V, capital A, capital B? Anybody?
Multiply by square root of 3,
Right.
and subtract 30, or add 30.
Yeah, add 30, right? So it'd be 50 plus 30 degrees, right? 30 degrees, or 80 degrees. Now that's VAB. What does it want here? Find the source voltage if the line impedance can be ignored. So that was it. Jessica, you have the solutions manual. Is that what it is? This is about 208 right here.
They didn't really find that one on the solutions. They just did VBN and then VCN.
Yeah, but that's the phase voltages. That's the actual VAB if it's in a. Well, okay, yeah, that's right. That's right. This right here that we have would be VAN, then VBN would be minus 120, and VCN would be this, and 50 minus 240 or plus 120. Agreed?
Mhm.
Okay, now, are you guys hanging on to this? How many we got left here?
24.
It's fading. Now I'm going to go into something a little more complicated. Well, you all see how I'm adding complexity slowly, right? Nothing, I'm not trying to do anything, just, leaps and bounds where we take 8 steps at once. Next thing I'm going to do, and I probably should do these in sequence. You can do 544. It's straight forward, and you should be able to do it. But 546 is what I'd like to do, okay? Can you all hear me? Now, before I do that, let me ask this. Does anybody have a question so far? We've covered 3-phase power. I mean, now we've gone through 3-phase power. We've also covered what? We've covered basic power analysis in circuits with complex power, with capacitors for power factor correction. I understand the quiz average is very high, according to my grader, even with all the zeros for people that didn't show up. So any other questions? I see the people just falling off like flies. Anybody? Before I continue along this train of thought. All right, now, this is going to be 546. Here, in case you don't know, it says in a balanced, and by the way, that word will repeat itself ad infinitum because you don't know how to do a non-balanced system. That would be where the loads are different values. That would be a much more complicated problem. In a balanced 3-phase Y delta system, so now right off the bat, you do Y delta, right? System. They say the source is VAN 120 at 10 degrees. Now you can draw that. It's plus to minus 120 at 10 degrees. And I'm not even gonna bother putting RMS on there. Then they say, and the load impedance per phase is 24 at 18. Don't write that out yet. Just put Z delta is 24 plus J 18 over here. All right, sorry. I'm putting it over here. That's Z delta. And then they say, if the line impedance is negligible, determine the line currents. This is more or less a gimme too. So we're always going to go to not Y delta, but what? We always go YY to get the line current. That's small a. That's then. Since there is no line impedance, this is just capital A. Then you have 24 plus J18. And by now, I think you guys got it. That's capital N. They want this. I think most high school students can probably do this if they've had any kind of electronics. This is what? Just voltage here divided by impedance. It's that easy. You agree with me?
Do I need to convert to YY?
I'm sorry, divided by 3. I didn't divide. Sorry, it's 24 plus J18 divided by 3. I'm so glad you said that. That was a delta load, so you have to divide by 3. And when you do that, what do you get? You get 8 plus J6, 6, right? So this is actually 8 plus J6. Thank you. So that means I here, small a, capital A, would be equal to 120 at 10 degrees divided by 8 plus J6, and whatever that is, it is. I got a question for you after you're done with that. Is everybody still with me here that I can see on the screen?
Yeah.
Yeah.
Okay, I hope people are. I got Dylan, Gabriel, Tanner, Luke, Brantley, Isabella, Caleb, Jenny, Jessica, and Joseph. If you're all there, good. All right, that's a magnitude and an angle, and if somebody wants to give that to me, it should be a negative angle.
Um, 12, negative
Right.
26.87.
Minus, say that again?
26.87.
I got the same thing.
You got it? Okay, good. That's IAA. And again, you'll notice that VAN is VAB because there's no line impedance. If line impedance was added, the only thing happens is this number goes up and the current's magnitude goes down. That's pretty straightforward. Now, if you look at 549, we're going to talk through this first. First, I'm assuming you can all see that, or you can look in your book because, or look in OneNote because this is up there in OneNote. In a balanced three-phase Y delta system, so it's Y and then delta, the impedance per phase of the load is that. So we know we're going to go Y, Y. This has to be divided by 3, and that makes that 7 plus J3. That's my point, correct, class?
Yeah.
Mm.
Then after that, and the source voltage is, now that's V, that's convenient that they left square root of 3. VAB is 120 at square root of 3 at 60 degrees. We want VAN, so we take 120 at square root of 3 and divide it by the square root of 3. And that brings it back to 120. And we take that value of angle and subtract 30, right?
Yeah.
So that means I got 120 at 30 degrees. And they got a line impedance there. So let me just draw this. This is 549. So for this one, it looks like this. We got, for the YY case, we'll get whatever they want in a second. We got 120 at 30 degrees. You can put this as small n if you want. That's capital A, I mean small a. Then they have the line impedance, I'm sorry. Here. They have a line impedance of 1 plus J1. So 1 plus J1 is this. Then that's capital A. And they have the load impedance, but it's in a delta configuration. So this is Z delta is equal to 21 plus J9, which means ZY is equal to 7 plus J3 ohms. Right here. And they want the line currents. I'm only going to get the A-phase currents. This current again here, which would be I capital A capital N, or I small a capital A, whatever you want to put it, is going to be equal to 120 at 30 degrees divided by simply 7 plus J3. Are you good with that, class? These are
Right.
RMS values. And you could see the next logical thing I could ask is how much power is dissipated at the source, real power? Anybody want to throw in how you would do it?
Just sum up the power dissipated by in the line and the power dissipated
No,
by
no.
the load.
If you want just the power dissipated in the load, the real power, anybody? It should be pretty obvious to you. I've got current, right? I've got a magnitude of current, whatever it is. Do you agree with that?
Yeah.
You can give me the magnitude if you want.
Mm-mm. 120.
No, remember, it's the magnitude of the current I want.
Oh.
So it's 120 over at 30 degrees over 7 plus J3. You can give me the whole value.
It's 15.76 at an angle of 6.8.
All right. Now, if you wanted the real power dissipated at the load, this is real power in kilowatts. This is an RMS value, right? RMS amps, correct? You would simply take I RMS at the load squared times the resistance, which is 7. You all follow me? How many see that? Right, I squared RMS times R. So we've got the magnitude is 15.76. Take that and square it and multiply it by the real part times 7. We could get the complex power if we wanted to, but I'm just asking for the real power. Are you with me?
Yeah.
Okay, good. I I think that's enough for today. And I think I got through all the homework problems, just about, didn't I, class?
Mhm.
Does anybody have any questions before I break it off? Because I'm here to help, so to speak.
For that I8 in there, do you not need to account for the line load?
Well, didn't I, for this one, right? Sorry, I'm so sorry. You're absolutely right. I don't know how, it would be actually 8 plus J4, pardon me. I'm very sorry about that. Thank you so much. So,
Wait.
because there's 1
Okay.
plus J1 and 7 plus J3 is the series value. Thank you. This would be I, capital A, capital N would be equal to 120 at an angle of 30 degrees divided by the series impedance, which would be 8 plus J4. That's exactly right. Thank you, whoever said that. Was that you, Luke, or who?
That's 13.42 at an angle of 3.434.
Say that angle again.
3.43.
All right, to get the power dissipated, you would take 3.42, square it, and multiply by 7, because 7 is the impedance. Y'all with me? Okay, does anybody have any further questions? And was that Luke who said that, or somebody else?
It was me.
Dylan, thank you. All right. Now, here's a question for you. We haven't talked about this. Let's see if you can brainstorm on this. Can you all see this problem right here, 551?
Yeah.
What's the equivalent impedance? If we wanted to take these two loads, one is a delta load that's balanced, the other is a Y load that's balanced, and we wanted to get an equivalent single load that represented them in a delta configuration, say. How would you do it? And give me the reasoning. Can anybody think of it?
Wait, so you're saying the delta load and the Y load are in parallel or in series?
Well, you look there, you don't even have to, isn't this, call that A, B, and C, right? Now,
Yeah.
there are two loads that are in parallel. Can you see it? That the A to B, B to C, and C to A connections are like, this load is all Y, this is delta, just by observing it. Do you all see that?
Yeah.
All right. Now, if we turn this one into a Y load, can you hear me okay?
Mhm.
If you turn this load into a Y, we would have what? Divide this by 3, we'd have
Yeah.
6 plus what? J2, correct?
Yeah.
6 plus J2 in the Y. So you would have two parallel Ys then, wouldn't you?
Yes.
You follow me? And so what this would look like, if you don't mind me showing you, for just the A phase, it would be A phase. Then you would have, the first one would be 4 here, and it's J1. And that would be, call it A, and this would be the neutral, or capital A, pardon me, and neutral. And then over here, when we do the Y business, we get 6 and J2. So they're in parallel, right? Hold on, I got someone at the door. All right. Thank you, Harper. Thank you. All right, good job, Harper. Sorry. That was Amazon. So what do you do with these to get an equivalent, guys? This would just be for the A phase. Anybody?
Just,
They're in parallel, right?
yeah,
So
just
I
add
could
them
take
like parallel resistors.
parallel impedances, right? You would take this times this over this plus this. You could say that Z Y equivalent would be equal to 4 plus J1 times 6 plus J2 over the sum, which would be 10, right? Plus J3, right?
Yeah,
Okay, and that would be one, that would be ZY, and Z delta would be that value times square times 3, correct, class?
Yes.
Okay. I'm going to show you one more thing while you're handling. This one I didn't get to, but it'll help you. This is the last thing. I got 4 people on. No, I got 3 people only beside myself. Dylan, you're hanging on. And wait a second. No, I got 4. Pardon me, 4. I got Brantley, Dylan, Jessica, and Joseph. Usually Jessica and Joseph are there at the very tail end, but the rest I can't say because frankly I don't hear them talking. Let's try that. All right. Now, here's the one thing I didn't get to. Suppose, I mean, I gave you enough information to do it, but I didn't do it. Suppose I had this. I have VAB equal to call this 208 at 0 degrees. All right. Then I had a Z delta equal to call it 30 at an angle of 10 degrees. All right. Now that is a delta configuration. Agreed, class?
yeah,
Now, if I draw that, and I'm going to just draw this, you don't have to. I'm going to say if I'm drawing a delta configuration, then you would have a voltage here. You'd have a voltage here. You don't have to draw it, just appreciate I'm drawing it. There's no line resistance or no line impedance. Then you would have a delta load here. Delta load here. It doesn't matter if they're upside down or right side up when it's delta. And this would be A, B, C. This would be capital A, capital B, capital C. So I would go here and I'd say this is small c to C. This is B. That's the symbol for jumping over a line to B and then A to A. That's the actual connection. Here I have VAB, pardon me, VAB here as 208 at 0 degrees. And here I have Z deltas at 30. All these are Z deltas. Right? Now take a careful look at this. If we take a look at A to B, because there is no line impedance, I want you to see this. There's no line impedance. A to B here directly connects between capital A and capital B. So if we just looked at the AB line voltage, we would have a series connection we'd have, or at least we'd have a connection where we had a voltage here. We'd have 208 at 0 degrees, and that would be connected to a load. Now that's capital or small a, small b, that's capital A, capital B. And this is Z delta, and this is 30 at an angle of 10 degrees. Do y'all follow me?
yeah,
I'm just showing you the A, B, Y, I mean delta phase of this in the load and at the sending end. Now this current here is the current that we've been calculating all the time. This current right here, and that would be I small a capital A, but we're going to use just the delta load, and the delta voltage would be equal to 208 at 0 degrees divided by 30, right, at 10 degrees. That means it's going to have a magnitude and the angle would be minus 10 degrees. Can everybody follow me on that?
Yes.
What do you get for this? Uh, 208 over 30.
6.933.
6.9 for now. Okay. Approximately. All right. Now, if we were to do this, remember this, that the AB phase voltage is not just across the AB load, all right? There's also what? Because this is a delta connection, AB phase voltage is also across what? B to C, C to A. So the currents are going to be different than, I mean, this current IA that we calculate is the line current, but the currents actually in the delta connection right here are going to be different. I'm going to show you in a second how to do that. I'm sorry. Let me correct myself. Sorry. Tell you what, let me say this. This is the current, and I said something wrong again. This is the current through AB, the AB delta. So I could say I delta. That's the current from A to capital B is, capital A to capital B is I capital A capital B, and that is 208 over 30 at 10 degrees, or it's equal to about 6.9 at an angle of minus 10 degrees. About. Now that's current flowing here. That's I capital A capital B. Do you follow me?
Yes.
However, that isn't this current. You have to add to it this current, IAC. You all follow me? Because this is a single node. Now, I'm not going to get into it right now, but the thing is that if we have this value of current, this current here will be up by the square root of 3. Remember before, VAB was increased by the square root of 3, and the angle was advanced by 30 degrees, right?
Yeah.
All right, that was for the voltages. For the currents, for this current, I, small a, capital A, you actually take this current's magnitude and multiply it by square root of 3. So you take square root of 3 times the magnitude of I, capital AB, and I'll say more about this next time. And then the angle will be decreased by 30 degrees. So it will be whatever theta AB was associated with that, or the current right here, minus 30. Now, I was going to spend time proving it, but because I've got 4 people only here, I won't. What I will do is take a look at my PowerPoint one more time, if you don't mind, see if I can show you the PowerPoint discussion of this. This is what I was doing right here. You remember I said equivalent, show the equivalence, and he does it right here. Somewhere, yeah, he comes down to Ry is R delta over 3. Really, it's Z delta over 3 is equal to Zy. Can you all see this, class?
Yeah.
Yeah.
That's the thing I was doing. And this is a delta to Y configuration. He's just showing you. I'm looking for one thing. This is a good problem. This is a Y to delta with a line impedance. But I wish he would have said it explicitly, unless I missed it. That's voltages. He doesn't have a phasor currents drawn, I don't think. That's what I'm looking for. Does he have them? Give me 1 second here. I'm going to draw these out next time for you. Now the currents, the angular difference between voltage and current in the different phases is always the same. I mean, in other words, if you have a delta angle of, say, if you've got a VAN at 0 degrees and you've got a current I, small a, capital A, say minus 30 degrees, just say that. Well, if you get VAB there, no, I'm going to confuse you with that statement too. I got to actually show it to you. This book doesn't have it. Drawn the way I'd like. I'll just show you this in an example, and then I'll cut it off here and I'll do it. I'm going to draw the relationship between the currents in the line, or the Y currents, and the delta currents next time. But if you take a look, this would be a delta current.
We're looking at the PowerPoint right now.
Oh my goodness. So if I take a look at this just for a second, suppose I have IAB, that would be a current in the delta load at a magnitude and angle. You follow me? Can you see that IAB here, right here?
Yeah.
Yes.
A magnitude and angle. Now, the actual magnitude of the line currents goes up by the square root of 3, and the angle is reduced by 30 degrees. All right. Remember, the voltage when you go from delta to from Y to delta goes up by the square root of 3. Current goes down by the square root of 3. So I'm in the delta. To get back to the Y, I'm going to multiply by the square root of 3. And you can see that happens right here. It's 42.44. And then the angle is going to be decreased by 30 degrees. Now, I'm going to go through this a little bit more and make it a little clearer next time, but that's really what I wanted to talk about. Are you guys good with that?
Yes, sir.
Yeah.
And the real thing is, if you really want currents, if you have voltages as across elements, you can, and impedances, you just divide voltage by impedance and you always get current, but it can be tricky. Now guys, any last questions before I cut out of here?
I have another test on Friday. So, like right before this, and I get double time on that one too. So I think
How
I'm
about, huh?
I think I'm gonna. So that class has an online test. So if it's easier for them just to shift that around.
Well, ask them and see.
Okay.
I mean, if they agree to it, great, but make sure, who's teaching?
Dr. Birch.
Oh God, I don't know if it would be easy. You better ask first.
Okay.
Tell him to take my class, see what he says.
All right.
I'd prefer you there. I mean, I can give it to you afterwards, but I prefer you there. And for Birch's test, I mean, I advise everybody this for any test, but for his especially, you got to be sharp and you got to get enough sleep.
Yeah.
Because he has tricky stuff.
Oh yeah, I know.
What about you, Jessica? Anything?
No, I'm good. I just have Six Sigma this week and lead and electrical test.
Okay. Now, no matter what I do,